In the last class, we discussed about the semiconductors. Semiconductors, wait. Coming to the semiconductors, I recall the semiconductors little bit. Coming to the semiconductors, our semiconductors are two types. One is intrinsic, and coming to the second, impure form, extrinsic semiconductors, right? Extrinsic semiconductors. Coming to the intrinsic semiconductors, we already learned about the intrinsic semiconductor. When the semiconductor in the pure form, we call as the intrinsic. So coming to the pure form, so example for pure form is germanium and silicon, only the two, germanium and silicon. So when they are in the pure form, so they act at low temperatures, intrinsic semiconductor act as an insulator. Why? Because when we see the configuration of germanium and silicon, both are having 4 free electrons in the outermost orbital. Germanium or silicon having 4 free electrons in the outermost orbitals. All the 4 free electrons are participating in the bonding. So due to participating in the covalent bonding, all the electrons are tightly bonded. That's why it acts as an insulator. So in the process of finding the conductivity in the semiconductor, we are going to add dopants to the pure form of semiconductor. So when the semiconductor is doped with the impurities like third group elements or fifth group elements, they are called as extrinsic semiconductors, nothing but impure form. Impure form. So when we dope it with third group elements, third group element, majority charge carriers are the holes. So that's why we named as p-type semiconductor. P-type semiconductor. When we dope it with pentavalent impurities or fifth group elements, so the type of semiconductor is n-type semiconductor. Already we discussed in the previous classes before the holidays. So in the same way, we are finding the intrinsic carrier concentration and extrinsic carrier concentration also. So coming to the intrinsic carrier concentration, to find out the intrinsic carrier concentration, we have to know what are the charge carriers in the semiconductor. So what are the charge carriers in the semiconductor? Both electrons and holes are the charge carriers. When we take in one semiconductor, and this is a conduction band and valency band. This is the valency band and this is a conduction band. So coming to the semiconductor, all the holes are available in the valency band. Holes are indicating with P and electrons are available in the conduction band. They are indicating with N. To find out the intrinsic or to find out the carrier concentration of semiconductor, we need to find out the number of holes per unit value of the material as well as number of electrons per unit value of the material. In the previous classes, we derived the equations for both N and P. So what is the equation for N? N equals to 2 into 2 pi me star kt by h square whole power 3 by 2 and exponential of EF minus EC by KT. So what is EF in the term? EF minus respond in the Respond through your chat box, Amma. Respond through chat box. Yeah, Fermi energy level. So coming to the Fermi energy level, in case of intrinsic semiconductor, both are it is having in between the bottom of the conduction band to the top of the valency band. So if bottom of the conduction band we are taken as EC and top of the valency band we are taken as EV. So the Fermi level exactly in between the bottom of the conduction band to the top of the valency band. In the equation, EF is the Fermi energy level. That Fermi energy level exactly in between the bottom of the conduction band to the top of the valency band, because the number of electrons are equal to the number of holes in the when it is in the pure form. So like that we derive the equation for P also in the similar way. We derive the equation for P, nothing but number of holes per unit value of the material. So when we multiply these two, we are getting the intrinsic carrier concentration, nothing but Ni. Ni equals to N into P. So the equation is 2 into 2 pi kT by h square whole power 3 by 4 and me star ms star whole power 3 by 2 and exponential of minus Eg by 2 kT. Minus Eg by 2 kT is the formula to find out the intrinsic carrier concentration. And this is the equation for number of electrons in the conduction band. This is the equation for number of electrons in the conduction band. After that, we derive the equation for P also in the similar way by taking the small energy portion within the valency band. We derive the equation for P. So after that, by multiplying these two, we are getting the equation for intrinsic carrier concentration Ni. So after that, by equating the two, we are going to find out the equation for EF, that is EF equals to EC plus EV by 2. These topics are covered in the previous classes. EC plus EV by 2. I got Fermi energy level. Fermi level exactly in between the bottom of the conduction band to the top of the valency band. So including these intrinsic semiconductor, we discussed about the extrinsic semiconductor also. Coming to the extrinsic semiconductor, we find the equation for R, we derive the equation for N-type carrier concentration as well as P-type carrier concentration. Coming to the N-type semiconductor, so when we do put with pentavalent impurities, so N-type semiconductor will be formed. So with the donor electrons. So donor energy level is presenting near to the bottom of the conduction, bottom of the conduction band. Again, I am taken semiconductor. This is the conduction band. Valency band. So top of the valency band, again I am taken as EV, E suffix V. Bottom of the conduction band is EC. So donor energy level. This is the donor energy level. We are indicating with ED, E suffix D. Number of electrons are available in the valency conduction band and number of holes in the valency band. P is available in the valency band. So ED is the donor energy level. So in case of N-type semiconductor, number of electrons are greater than the number of holes. That's why Fermi level also not lies in the middle of the bottom of the conduction band to the top of the valency band. It's shifted to near to the conduction band. So when the Fermi energy level is shifted near to the conduction band, we are going to derive the equation for EF. So to derive the equation for EF, we are taken the number of donor electrons ED or N suffix D is equal to number of electrons in the conduction band at very low temperatures. At very low temperatures, the number of electrons available in the conduction band are equal to number of donor electrons or ND or capital ND. ND is the donor concentration. So donor electrons are available in the donor energy level. So at the very low temperatures, the number of electrons in the conduction band are equal to number of donors in the donor energy level. By equating these two, we are going to find out the equation for EF. What is the equation for EF? So we are getting the equation in terms of donor electrons, ND 2 ND whole power 1 by 2 and 2 pi me star kT by square whole power 3 by 2 exponential of ED minus EF by kT. We are getting that equation. By substituting in number of electrons equation, we are going to find out the n-type carrier concentration or number of electrons in the conduction band in case of n-type semiconductor. So what is the equation for number of electrons? Conduction band 2 pi star kT by and this is the equation gives the number of electrons the energy level is formed near to the EA and level for EF. Is I audible? అమ్మ వినిపిస్తుందా? Amma, is I audible? Right, for rule number 4, 48 responded. Okay, Amma. So due to unstable internet connection, so it's got some disturbance. Sorry for that. So coming to the discussion. So coming to the n-type p-type semiconductor, again p-type semiconductor Fermi energy level is shifted to near to the valency band EC, and this is the Fermi energy level for n-type, and this is the donor energy level ED, and top of the valence band EV. This is the acceptor energy level EA. So this is the Fermi level at low temperatures, the Fermi energy level for p-type semiconductor. EF equals to EA plus EV by 2. So this is a Fermi energy level in case of n-type semiconductor. EF equals to EC plus ED by 2. ED by 2. So up to your internet connection is unstable. So up to N-type carrier concentration and P-type carrier concentration, is it clear to everyone? Please respond by raising your hand or by sending message through chat box. Please respond. 12, 60 to 48 responded. 20, 58. These people only. I think all of you new to the Zoom classes, right? Nothing to worry. So only 7 students are yes, sir, right? 56 is sir. 65, 28, 50, 61. Okay, good, no problem. So coming to the continuation of the class, we are going to discuss about the Hall effect now. So after that, we have to complete the variation of Fermi energy level for N-type and P-type semiconductor. So coming to the class, wait for 1 minute. I'm going to download the PPT. Is the PPT is visible to everyone? Is the PPT is visible? Yeah, right. Thank you. And 1 or 2 response are enough. See, all of you keep the heading Hall effect. This is about extrinsic N-type semiconductor. After that, P-type semiconductor. Coming to the Hall effect. All of you try to keep the heading Hall effect. One of the important topic. In this class, we are going to cover this Hall effect. Slideshow. So coming to the Hall effect, try to listen to the definition very carefully. When a piece of material placed in a transverse magnetic field. Wait, there is a meeting coming to. So coming to the Hall effect definition, when a piece of material, I am taken on piece of material, either metal or semiconductor, if it is N-type and P-type semiconductor, piece of material placed in a transverse magnetic field, So electric field will be produced EH. Electric field will be produced perpendicular to both magnetic field and flow of charge. So electrons flow is in this direction when the field is applied. When the field is applied, what will happen? Potential is applied, flow of electrons in this direction. So when this piece of material placed in a transverse magnetic field, what will happen? Electric field will be generated inside the material. That generated electric field is perpendicular to both magnetic field and flow of charge and current. So this is the definition of Hall effect. Again, I am repeating, when a piece of material placed in a transverse magnetic field, what will happen? So due to generation of potential difference between the two sides. So when the potential is applied, when the potential field is applied, due to the force acting on the electrons, all the charge carriers are accumulated to one side. So when the charge carriers are accumulated to one side, what will happen? Potential difference is creating between the two ends. This is the phase 1 and this is the phase 2. Between the two phases, what will happen? When the field is applied, potential is applied, potential difference is creating. Due to the potential difference, electric field is generated inside the material. So that generated electric field or voltage developed across the material, that voltage we are calling as a Hall voltage. So the generated electric field perpendicular to both magnetic field as well as flow of charge. The definition I am going to share now. This is if a piece of semiconductor carrying current I is placed in transverse or perpendicular to the magnetic field, then an electric field EH is generated in perpendicular to both current and magnetic field. Hence, production of Hall electric field EH. So due to that electric field, what will happen? All voltage developed across the material, because of when the force is applied, when the potential is applied, all the charge carriers are accumulated to one side. When the charge carriers are accumulated to one side, what will happen? Potential difference is creating between the two ends, like phase 1 and phase 2. So when the potential difference is creating, voltage is developed across the material. That developed voltage we are calling as a Hall voltage. So that voltage and electric field, generated electric field, both are perpendicular to current and magnetic field. So this is called, this effect we are calling as a Hall effect. See again, once again I am repeating the definition. All of you try to understand. If a piece of semiconductor, either it is conductor or semiconductor, whatever it is. So if a piece of material carrying current is placed in transverse magnetic field, what will happen? What we are going to observe? EH is electric field is generated. That the generated electric field is perpendicular to both current and magnetic field. That is called as a Hall electric field. So due to that electric field, what will happen? So voltage developed across the material. The developed voltage we are calling as a Hall voltage. That voltage and electric field both are perpendicular to both magnetic field and flow of charge or current. So this is the definition. So in this in this Hall effect, we are going to derive the equation for VH and EH in terms of B and I. Okay, this is a diagram for that. So this is a phase 1 and phase 2 here. When the electric field is applied, when the potential is applied, so what will happen? Due to the force acting on the electrons, what will happen? All the charge carriers are accumulated to one side. So when the charge carriers are accumulated to one side, the potential difference is creating between the phase 1 to phase 2 to phase 1. So due to that, a voltage developed across the material, that voltage we are calling as a Hall voltage. Again, this is a diagram. So in the y-axis, we are applying a magnetic field. In the x-axis, flow of charge carriers are, we are current is flow of charge. So in the z-axis, we are going to observe Hull electric field. So assume an n-type semiconductor and let I be the current passed through the x-axis, and let be the magnetic field applied to the z-axis. Due to the current I, the flow of electrons, the force acting on the electrons in opposite directions to the direction of conventional current, and due to the magnetic field B, there is downward force act on each electron. That force we are taken, magnetic force we are taken as B into E into V. So in the z-axis law, current flow of electrons in the occurs in the z-axis direction. So negative charge accumulated to the bottom base. So here we are taking electric field and magnetic field. What happened? 1 second, Amma. It is not connecting. So here electric field we are taken as FB. So magnetic field B into E into V, and force due to the electric field FE equals to E into capital E. So by equating these two, we are going to find out the equation for EH. E into EH equal to B into E into V. By cancelling these two, we are going to find out the equation for EH equals to B into V. So after that, we are taken the current density J equals to N into E into V. So from that equation, V equal to EH by B, EH by B. So therefore, current density J equals to N into E into EH by B. So from that we derive the equation for EH. What is EH, Amma? Electric field generated inside the material, BJ, B into magnetic field, and the current density into N into E. And this is the equation for EH. So derive the equation for EH. What we have taken? The forces acting on the electrons due to magnetic field and due to electric field. So due to the magnetic field, what is the equation? B into E into V, and due to the electric field, E into EH, charge into applied generated electric field. So that's why we are indicating EH, E suffix H, Hull electric field. So by equating these two forces at equilibrium position, what will happen? The two forces acting on the electrons are equal. By equating these two, I'm going to find out the equation for velocity V, so potential V. So after that, the current density J equals to, we know that equation, N into E into V. So by substituting equation for V, I'm going to find out the equation for EH. EH equals to BJ by N into E. So the same equation I'm writing it as EH equals to RH into BJ, where RH is the Hull coefficient. Where RH is the Hull coefficient. Hull coefficient. So from that Hull coefficient, RH equals to 1 by N into E. 1 by N into E. So from the Hull coefficient, we can identify the type of material. So if RH is negative, the type of material is N-type material. If RH is positive, in the experiment, in the if you are getting Al coefficient is negative, so we can say the type of material which we used uh, in the experiment is N type. If Al coefficient is positive, so we can say the type of material is P type. Means using the Al coefficient, we can identify the type of material. That is the application of Hall effect. The later we discussed about the applications. So try to listen or try to understand. The equation for H is Bj by N into E. So the same equation I am writing it as RH into B into J, where is dependent RH equals to 1 by N into E. So by getting all coefficient is type, and by getting positive, we can say that or derive the equation for Hall voltage developed across the material. For that, I am going to see. Potential difference is due to the electric field is E into EH. So under equilibrium condition, what will happen? Upward force due to electric field equal downward force due to magnetic field. By equating these two, I am going to find out the equation for V. V equals to EH by B. So after the current density, we know that the equation for current density equals to N into E into V. By substituting V equal to EH by B, I am going to find out the equation for EH. EH equals to J into B by N into E. So I am define the Hall coefficient from that equation by taking 1 by N into E equals to RH. So P is the whole here RH equals to 1 by N into E for electrons, RH equals to 1 by P into E for holes. So EH equals to RH into Bj. This is the relation between the electric field and Hall coefficient RH. So from that RH equals to EH by Bj. So after that, it is not clear, Amma. Wait for 1 minute. All right. I'm going to share that. Wait a minute. Sorry. So the RH equals to EH by Bj is the equation to find out the Hall coefficient. RH, that is the relation between the EH and RH. So after that experimental determination of RH, so all of you try to note down or take a screenshot of these 3 slides. These 4 slides. First slide is the definition. Try to take a screenshot. First slide related to the definition. So after that, second slide is the diagram only. So coming to the third relation between the RH and VH. To find out the relation between the RH and VH, so I'm going to consideration of electric field, force due to electric field and magnetic field. What is the equation per force due to the magnetic field V into E into V. So after that, due to the electric field, force acting on the electrons are E into EH. So under equilibrium condition, what will happen? The upward force or due to electric field or due to magnetic field, the force acting on the particles are equal. By equating the two, I'm deriving the equation for B. So after that, by taking the current density equation and substituting the equation for V, I'm going to find out the relation between EH and RH. What is EH? Electric field generated inside the material in the Hall effect, and RH is the Hall coefficient. So Hall coefficient is defined as 1 by N into E. So for the by getting Hall coefficient is negative and positive, we can identify the type of material. If it is the negative, we can say the type of material is N type, and if it is positive, the type of material is P type. So and after that, EH equals to relation between the RH and EH is RH equals to EH and BJ. So after that, experimental determination of RH. So we know RH equals to EH by BJ. So coming to the VH, all voltage across the material, if the thickness is T, so generally the equation for V is E into D, or EH equals to D is thickness we are taking of the material, thickness we are going to take in. So EH into T. So from that, EH equals to VH by T. And if small b is the width of the sample, area is A and thickness is T. What is the relation between the area and breadth and thickness? Area equals to breadth and into thickness B into T. So after that, again current density J equals to I by A. So I'm going to substitute A equals to B into T. So we are getting J equals to I divided by B into T. So in that equation, RH equals to, we know the EH and BJ na. So I'm going to find out the equation for A separately and equation for J separately, right? So by getting the EH equation separately and J equation separately, I'm going to substitute now. So here VH by T is the equation for EH, and J equals to I divided by B. I'm going to substitute here J equals to the equation for which is VH into B divided by capital B into I. Here VH is the Hall voltage developed across the material and B is the breadth of the semiconductor, and capital B is the magnetic field, I is the current due to the flow of electrons. So from that, I am writing the equation for VH. Hall voltage developed across the material is RH into B into capital I by B. And these are some applications about the Hall effect. All of you try to take a screenshot of this one also, fourth slide. No need to note down. All of you try to take a screenshot. After that, try to follow that screenshot somewhere. Again, from the determination of Hall coefficient RH and Hall voltage. So for that, we are the determination of Hall coefficient and experimental determination of RH. For that, I am going to consideration of thickness and area of the material. This one also, try to take a screenshot. So is the derivation is clear to everyone, Amma? I think it is not clear to everyone. If it is clear to everyone, I am going to stop the class today. because of the next class and faculty is waiting. It's 11:10 already. Please, by raising the hand, respond all of you. Only 48 is responded. 15, 16. Okay, so many students are responding. Okay, thank you. So in the next class, we have another class today. So in the next class, learn clearly about the all effect in the next class.